States of matter and phase changes. States of matter. Strong particle bonds help solids to keep their shape and resist flow. The strength of these bonds determines hardness, melting point, and how much a solid expands when heated. Impurities can change a solid's strength, hardness, color, conductivity, and melting point. In metals, small amounts of impurities form alloys that are stronger or more durable. For example, carbon and iron make steel, while too many impurities can weaken or make a solid brittle. There are two different types of solids. Crystalline solids have an ordered structure, like in salt, diamonds, metals, and amorphous solids have a random structure, for example, glass, plastic, wax. Liquids are a state of matter where particles are close together but not fixed in place. The bonds between them are weaker than in solids, allowing the particles to move and slide past each other. This gives liquids a definite volume but no fixed shape, they take the shape of their container. Liquids can flow, are hard to compress, and have moderate density. Their particles are held together by moderate forces, showing some order but not rigidity, with small spaces between them that allow vibration and free movement. Because of this, liquids can flow and be poured easily. When heated, particle motion increases, reducing viscosity and making the liquid thinner. When cooled, motion slows, increasing viscosity or causing freezing. Impurities can alter a liquid's boiling or freezing point and its viscosity. There are two main types of liquids: pure liquids, made of a single substance, like pure water, and mixtures or solutions, which contain dissolved substances, like salt water or juice. Gases are a state of matter where particles are far apart and move freely in all directions. The forces between them are very weak, so gases have neither a fixed shape nor a fixed volume, they expand to fill any container. Because their particles move quickly and are widely spaced, gases are easy to compress and have low density. Their behavior changes greatly with temperature and pressure, as seen in air, helium, and carbon dioxide. Gases are made up of atoms or molecules that are far apart and have weak or no bonds between them. They have no fixed shape or volume, low density, and are easy to compress because their particles are spread far apart and move rapidly in all directions, colliding often and randomly arranged. Gases expand when heated and contract when cooled, and pressure increases when particles collide more frequently, such as in a closed container. Their temperature, volume, and pressure are connected by gas laws like Boyle's and Charles's laws. Impurities or mixtures can affect a gas's pressure, flammability, or reactivity. There are three main types of gases: elemental gases, made of single elements like oxygen, O2, or hydrogen, H2, compound gases, made of molecules with different atoms such as carbon dioxide, CO2, or methane, CH4, and mixtures, which are combinations like air, composed mostly of nitrogen and oxygen. Plasma is a state of matter similar to gas, but its atoms are ionized, meaning they have lost or gained electrons. When most atoms in a gas become ionized, the gas turns into plasma, made up of positively charged ions and free-moving electrons. Even though it has charged particles, plasma is overall electrically neutral. On Earth, plasma appears in lightning, but it makes up most of the universe's matter, including stars. This ionization process gives plasma unique properties that make it behave differently from solids, liquids, and gases. Plasma is a state of matter made up of a mix of ions and electrons that are not bound together like atoms in a solid or molecules in a gas. It is electrically neutral overall but conducts electricity and responds strongly to magnetic and electric fields. When energized, plasma glows, seen in lightning, stars, and neon lights. Its particles move freely and extremely fast, with electrons moving more quickly than ions because of their smaller mass, and they collide often. These charged particles make plasma behave differently from gases, forming currents and waves under magnetic or electric influence. There are two main types of plasma: natural plasmas, such as those found in stars, lightning, and auroras, and artificial plasmas, created in neon signs, plasma TVs, and fusion reactors. Phase changes. A phase change, or transition, occurs when a substance undergoes a change in state on a molecular level. In most substances, changes in temperature or pressure result in a substance phase change. There are several processes of phase changes, including fusion, solidification, vaporization, condensation, sublimation, and deposition. Two-state changes are sublimation and deposition, solid and gas. Sublimation is when a solid changes directly into a gas without becoming a liquid. This happens when temperature or kinetic energy increases enough for particles to overcome the forces holding them together, or when pressure is low. The reverse process, called deposition, occurs when a gas changes directly into a solid. Under low pressure, vaporized materials form thin solid films on surfaces through methods like plasma sputtering or vacuum evaporation. Then, there's solidification and fusion, liquid and solid. Fusion, or melting, happens when a solid turns into a liquid as heat gives its particles enough energy to break the strong bonds holding them together. Solidification, or freezing, is the reverse process. When a liquid cools, its particles lose energy, move less, and lock into fixed positions, forming a solid structure. There's also condensation and vaporization, gas and liquid. Vaporization happens when a liquid changes into a gas as heat increases the particles' kinetic energy, allowing them to overcome the forces holding them together. Condensation is the reverse process, where gas particles lose energy as the temperature drops, causing them to slow down and stick together, forming a liquid. Finally, there's ionization and deionization, plasma and gas. Ionization occurs when a gas changes into plasma. As temperature or energy increases, gas particles gain enough kinetic energy to lose or gain electrons, forming positively and negatively charged ions. This creates a plasma, a gas-like state made of charged particles. Deionization is the reverse process, where ions recombine as energy decreases, turning the plasma back into a neutral gas. A Bose-Einstein condensate, BEC, is a special state of matter formed when a gas of certain particles, called bosons, is cooled to temperatures near absolute zero. At this point, the particles lose almost all kinetic energy and begin to behave as one single superatom, sharing the same quantum state. This means they move in perfect unison rather than as individual particles. Predicted by Albert Einstein and Satyendra Nath Bose in the 1920s and first created in 1995, BECS allows scientists to observe quantum behaviors, like wave interference and superfluidity, on a visible scale, offering deep insights into quantum mechanics and atomic physics. A Bose-Einstein condensate, BEC, forms at extremely cold temperatures, just above absolute zero, around -273 degrees Celsius, where atoms slow down almost completely. It is made only from bosons, particles that can share the same quantum state, such as rubidium or sodium atoms. In this state, all the particles act together as one giant wave or single quantum entity, showing quantum unity. BECS have unique properties like superfluidity, coherence, and wave-like interference patterns. They are scientifically important because they allow researchers to study quantum mechanics, superfluidity, and potential applications in future technologies such as quantum computing. Time crystals are a newly discovered phase of matter where particles move in repeating cycles without using any extra energy, like a clock that ticks forever without batteries. First theorized by Nobel laureate Frank Wilczek in 2012, time crystals repeat in time just as normal crystals repeat in space. They were recently created using quantum computers, like Google's Sycamore chip, and even visible liquid crystals. In these systems, particles continuously flip or swirl in stable, rhythmic patterns, breaking the usual rules of equilibrium physics. This discovery opens new frontiers in quantum science, materials research, and potential applications in data storage, anti-counterfeiting, and quantum computing. Time crystals are a unique quantum phase of matter that exhibit self-sustaining motion, continuously oscillating or moving in repeating patterns without any energy input. Unlike regular crystals, which break spatial symmetry through their ordered atomic arrangement, time crystals break time symmetry, existing in a non-equilibrium state. They can be created using quantum computers, lasers, or light-driven liquid crystals under carefully controlled conditions. Scientifically, time crystals provide new insights into quantum physics and the behavior of many body systems beyond equilibrium. In the future, they could have applications in quantum information storage, secure anti-counterfeiting materials, and advanced computing technologies. These are my sources. Thank you.